Hello everyone, today we are gonna do a parameter example. The main purpose of the lecture today is learn how to create a parameter and how to optimize the parameter that we created. I have prepared a table for you which has force that will apply and some properties here. The geometry which we'll design will be a beam. I didn't add the beam with 3D because it will be same as the last video. The only difference is dimensions. We'll go on with a simple beam. Our purpose today is to learn how to create parameters and get some experience with the mechanical section. Um, the force is 50 kilonewton, which is too much. We'll assume that 50 kilonewton is also a big force. The length will be 2000 millimeter, height is 60 millimeter, and the thickness of the beam is 20 millimeter. Young's modulus is given as 210,000 Newton millimeter square. Poisson's ratio is given 0.3, and allowable stress is given as 245 Newton millimeter square. So we'll give a comment in accordance with the yield stress. Now we'll work with the beam according to information above. Define a material. Create a geometry with design modeler, meshing with the default settings, fix one surface and apply a force minus positive y-axis on the opposite surface. See deformations, normal elastic strain, normal stress, and equivalent stress. I have prepared some steps like that will improve the design. And then for the final step, I will optimize the parameter values, the value which is safety factor with the minimum value of 2. And okay, all right, let's get started with defining material. We are going to workbench interface and open a new plate. First of all, I need to check the unit systems from here and then double click on engineering data. Okay, click here to add new material. You can give a name that you want, like beam. And after you gave a name, so what do we have? One is Poisson ratio, and the other one is Young's modulus, which we can find them in isotropic elasticity. We can write it like that. If the unit system here are not changeable, check and enable display values as defined option, as I told you before. The Young's modulus was 210 thousandths, which I remember, and the Poisson's ratio is 0.3. Let's type it. So we define the material, we can close it from here. Our next step will be creating the geometry. We need to see the properties, so let's go view and tab and enable properties and check analysis type and open design modular. Let's check our geometry while design modular is opening. The length of the beam is 2 meters, which will be x-axis. Y-axis will be 60 millimeter and z-axis will be 20 millimeter. You can change the axis. I will use these axes. In fact, I will ensure the coordinate system to be located on the bottom left edge of the geometry. What do we check first? Correct, unit system. Look, here meter degree. Let's change it to the millimeter. After that, you can go on the XY plane and create a new sketch yourself. Or from create a section, you can select a box. The box has appeared, as you can see. The properties are here. And now let's type the dimensions here. and we have 20 millimeter. Let's generate it and see what we got. Now, please look at her. By the way, I already taught you how to zoom in and out. Every mouse thing that you can in the mechanical section is also usable in design modular. And then now, now I wanna change my origin from here to here. Why did I want to change it? Because in generally we are sketching the geometry of the beams, trusses, structural constructions, iProfilm, etc. as a line in SolidWorks or AutoCAD. So we are sketching lines, and then I draw, for example, eye profile. The origin will be at the center of the eye section. We'll select line bodies for these lines. I have mentioned that before. That's why let's assume this geometry like that to get used to it. Uh, that's why we are sketching the lines, and then the origin will be at the center of the eye section. Okay, so we need to arrange the coordinate systems here. So we can arrange the coordinate systems from here. We don't need to move on x-axis. On y-axis, we need to move 30 millimeter because the high is 60 millimeter, but we can't move the coordinate system. The body will move, that's why it should be 30 minus millimeter. And minus 10 millimeter will be for z-axis. And then let's generate it and see what will happen. Alright, everything is okay, so that's it for design modeler. It was so easy to create this shape. And then let's exit from here. Let's double click on the model section and wait for it. Okay, it's opened. What was the current step now? Meshing with default settings. Before we go to meshing, geometry is here, and we can change its name with pressing F2 button, and don't forget to use just English alphabet. Now from here we need to change the materials from structural steel to material that we defined. Okay, we assigned it. Look, we can see from here that which material we defined and what are the properties of the material. The coordinate system is a global coordinate system. Now let's generate the mesh with default settings. Okay, the meshing process is done. Now, if we continue, we'll get a warning because we need to divide the surface at least two pieces, or you can say two layers. That's why let's change the default settings a little bit. Come to sizing section and check your use adaptive sizing option should be yes. If it's not, please change it. Then there is a resolution section here. But if you are using old versions of Ansys, I suppose this section should be relevance or something else. If you are using relevance right now, please approach 100. I mean go to the right. If you are seeing the same screen now, set the resolution value as 5 and regenerate the mesh. It will ensure us finer mesh structures. As you see, mesh quality is better than the other. We need to apply loads right now. Let's see what was the boundary conditions. Fix one surface and apply a force on the opposite surface, and the force is 50 kilonewton. We'll apply a force positive y-axis. Zoom into the surface and select the face, and after that right click and select fixed support. This surface is fixed. So it has 0 degrees of freedom now. That means the surface which is fixed cannot move on x, y, and z axis, and also cannot rotate in these axes. I mean, it cannot rotate around x-axis, y-axis, and z-axis. We'll see these various support types of details later. For the opposite face, click static structural and then select first and select the face, and don't forget that the face option should be selected and apply the geometry. Change vector to component and type 50,000 Newton in Y component. Alright, and now okay, we applied the boundary conditions. Let's go to the solution section. What do we want to see in results? Deformation, normal elastic strain, normal stress, and equivalent stress. And firstly, let's select a total deformation and under strain, pick normal, and under stress, select equivalent stress and normal. We can right click on solution and select solve. Now we are waiting as is to solve it. We'll get a warning because we applied too much force. It will warn us to check your deformations thoroughly. Okay, we've got the warning here. And then now let's see the total deformation. If unit systems are different, you can change it from here. And then let's check our deformation is too much. Deformation is 1762 millimeter, which is impossible. Just look at the true scale. Do you think it's possible? Because we applied too many forces. Just watch the animation anyway. Okay, this is impossible a movement. And then let's check our equivalent stress. It's 8,563 megapascal. Man, it's too much. What did we do? You can check the other results. I don't want to do that. I just want to change my force that I applied. And I applied a big force, and I wonder what we'll have again. And then the deformation change is 170 millimeter. Equivalent stress is 856 megapascal, which is still not acceptable. And actually, why is not acceptable? We all know it's not acceptable, but also the problem says the allowable stress is 235 megapascal. But we found it 856 megapascal. That's why actually that's why we can say it's not acceptable. Uh, let's reduce our force again to 2500 Newton and let's see what will happen. Okay, we are waiting for it. Okay, it's solved. And the stress is 428 megapascal and it's still not acceptable. Let's change our force one more time. I don't want to waste your time anymore. This will be last. I promise. And then we'll see the deformations and stress values again. Okay, the deformation is 35 millimeter and the stress is 175 megapascal. And then what was our value, the allowable stress was 235 megapascal. So we are in limits now. And let's calculate the safety factor then. 235 divided by 171. The safety factor is 1.37. The safety factor is at least 2 in the most real-world applications. That's why we have to develop our geometry or reduce the force. And also we reduced the force many times. I mean, we reduced our force again and again to find an acceptable stress value, right? But this can take too much time for complex geometry. Now we are assuming the force is 1000 Newton and we have to improve the design to get a safety factor is bigger than 2, under 1000 Newton force condition. Now I will show you how to do that. But first, what were the steps? Determine the parameter and improve the design. So we are gonna see that. Now, let the mechanical section down and open the workbench. To create a parameter, we need to open design modular again. How can we reduce the stress value? We can give a smaller length, but let's assume it has to be 2 meters. What can we do? We can increase the thickness of the beam so we can get smaller stress as well. And let's do that. Here and then also here is the question of how much should I increase the thickness? To get the answer, we'll create a parameter. So we don't have to change the thickness and analyze again and again. Change the thickness, solve again like we did for force. It was so boring, right? We'll define a parameter once and Ansys will give us the answer. So here's the question. How can we define a parameter? Okay, now here are properties of the body. And then we will examine the changes, the stress value according to change in thickness. So let's click this box to set a parameter and it wants us to give a name. Just type something that you want, but don't forget that. And also now we have details here. Since we have arranged the origins as a value, it needs to change also according to the value of thickness value to get the origin on the center of the beam. That's why we need to change these values, and also that's why we need to set this as a parameter and give a name. After that, we can exit from here. There should be a parameter set like that. You'll see it like that. And we can give a name. Let's double click on it and then P1 is the input parameter with a name of thickness and value of 20 millimeter. So we need the alt parameters right now. And this P2 value is minus 10 millimeter. How should we define it? It will be half of the thickness, right? That's why we need to set like we are using Excel from here. Just type P1 divided 2. But don't forget the minus. Let me type minus. Have you realized the change? It's not changeable anymore. So we defined our input parameters. What do we want to see as results? I mean, what will I examine when I change the thickness? Equivalent stress for maximum value, right? Let's go equivalent stress and find maximum and under results and select the box next to it. There is P in the box anymore. That means it will automatically go to the parameter section. We have also output parameters anymore. And now we'll change the thickness and look at the stress values. But we also have to take care of safety factors as a minimum too. And can we add manually the safety factor in the parameter? Yes, we can. But first, let's learn to use parameters like that. Basically, we gave the input parameters and we'll get a result as output. In the table of design points section, let's see if the thickness will be 25 millimeter, what would happen, and 30 millimeter and 35 millimeter. To get these results, please click Update all design points. Click here and say yes. Okay, here are results. When the thickness is 25 millimeter, Z coordinate happened 12.5 millimeter, and the maximum stress value reduced to 137 megapascal, and then 150 megapascal and 98 megapascal. The allowable stress was 235 megapascal. If the safety factor will be 2, so we need to get a value that is bigger 245 over 2. So I can accept 30 millimeter as thickness. But 5 millimeter gap can be too big for some products. If I have to give a value of maybe 1.1 millimeter, so this table will be going too long. And since the solution process time will change according to your computer speed, we might lose too much time. Uh, we need to prevent this. To prevent this, firstly, let's delete these ones. And now let's learn how to find optimized values. We can close the parameter. We found an acceptable value and assume thickness will be 30 millimeter. Now let's optimize these values in accordance with safety factor. And then now from toolbox, scroll down and find response surface optimization. And now drag it to under the parameter set. Okay, now we will give some conditions to software and it will give us the optimized values. Firstly, double click design of experiments. Okay, to optimize the thickness of the beam, we need to make some definitions according to finite element methods. That's why, okay. Firstly, just click design of experiments, and after that, make sure that the design of experiments type is central composite design. After that, as you see, thickness is defined here, and we will arrange lower bound, which means the lowest value. Arrange it as 20 millimeter. For upper bound, let's say 60 millimeter. Now, Ansys will give us the most appropriate values between 20 millimeter to 60 millimeter. And to get these results, we need to update this section. First, let's update this section. Of course, that's not all. We'll continue. You can see the process from here also. You can examine here and see process and see what's going on. Alright, we got the results. Here we can see the values for 40, 60, 30 and 50 millimeter. But we can get these results in the parameter. This is not our purpose to use this section. So let's exit from here. And now response surface needs to be refreshed. So let's go inside. We see the charts here. And to see these charts, we need to update it first. So let's update it first. By the way, I'm stopping the record when I click solve or update because of my laptop speed. Probably you realize that. And then I'm cutting these sections, of course. And now, okay, it's ready. Go for response and give attention to the chart. X-axis represents the thickness and y-axis represents z coordinate, which I don't mind about it. And I will change y-axis from coordinate to stress. As we expected, stress value is going down while thickness value increases. And now the value was 235 megapascal, so we can accept the values of half of it for the safety factor is 117.5 megapascal. And you can examine the chart from here. You can see the all values on this chart. We will get a results around here, but we need to get precise results, exact numbers we need. Let's exit from here and go for optimization section. Now here method name is screening and there's a number of samples that we can change it. And as you see here, we can change these ones. Let's go for objectives and constraints. Now we are making the optimization, guys, finally. And we defined necessary values in design of experiments and response surface. And now we are in the last step. We will define the constraints now. Okay, first select parameter from here. Now, for example, what are we expecting for stress value? Type should be no objective. Let's look the constraint. And you can see the options here. Remember that the upper bound was 60 and the lower bound was 20 millimeter, but we didn't arrange for this stress value. So what should we choose? Please think about it. We need to choose the values should be equal or bigger than the lower bound, right? We can define the lower bound as 0. That means stress can be minimum 0 megapascal. So no force. And okay, we determined the first condition. What can we determine else? I think we can do something for thickness. We can arrange it to minimize. I think I'll from here select minimize. And we've talked about the safety factor. And to arrange that, let's go back to parameters. Let's add a new parameter here. You can give a name with clicking on a new name, and then let's say it's a safety factor. After that, give the value to yield stress as 235 megapascal. I'm typing it, and 235 megapascal. How can we calculate the safety factor? So is right. It should be P5 over P2. I mean P5 divided by P2. It's 1.3 for the first values. And to see these changes in the optimization section, we need to update it again. I closed it and let me say update. I hope so far so good. Okay, it's updated. Let's go optimization section. Safety factor should be here, and let me add it. We need to define constraint for it. We will say the value should be equal or greater than the lower bound. And the lower bound should be, I don't know, the lower bound should be 2. Yes, 2. That means the safety factor will be equal or to greater than the value of 2. Let me give you brief information about what we did. First, we defined the equivalent stress, which will be greater than value of 0. Thickness, we set it to choose the minimum value for the safety factor. We set it to find a value which is greater than 2. So the safety factor will be minimum 2 and stress will be minimum 0 and the thickness will be the minimum value. This is what we did. And we gave all these constraints and Ansys will give us the optimized value. To solve this problem, we need to update it and then we will get the results. First, let me update it. And the results will be here. They are coming. We are waiting for it. I think this record is too long for the first videos. Sorry about that, but I had to show these properties to you. For the next video, we will make an example again with parameters, but don't worry, it will be easier. But we will work on 2D geometry. Okay, here are the results. Let's click candidate points here. Ansys gave us, actually you can see the results. You can see the results here. And Ansys gave us another 2 results here with variation from reference. Reference is the values that we defined. As you can see, the best value is 28.02 millimeter for this problem. I told you when we are looking at the charts as it will be around here, and now it's around there. But Ansys gave us the exact value, right? It's 28.02 millimeter. If I right click on candidate point 1 and select verify by design point update, we approve this solution. So after some time you can see the values whether accepted or not. And now we are waiting for it. My laptop is working a little bit slowly. Sorry about that. Okay, as you can see, it's verified now. Alright, that's it for today. We worked on the parameter and optimization section. You can save your files from here and then you can save as an archive. Stay tuned.